at PACCAR in Mount Vernon, Washington. He's currently working on Super Truck 2 project and other advanced heavy-duty technologies. He's a product of the University of Wisconsin as well. His title today is Improving Engine Efficiency in Heavy-Duty Truck Engines. Is there anything left to do? So let's welcome Steve.
Good morning. Thank you. I'm Steve Ciatti, as Rob mentioned, and I work out at the PACCAR Technical Center. Is there anything left to do at this point? Or, I mean, quite honestly, you listen to the news, and I'm sure if you've heard Kelly Senecal speak, I should probably just go home and call it a career at this point, because engines are dead technology, and there's no point in bothering with them anymore. Everybody's going to electrify everything, and it's the silver bullet that saves everybody, and I can just pull the eject handle and call it good, right? Well, maybe not. I think that you'll see, hopefully, by the time I'm finished speaking to you today, that in particular in the heavy-duty space, electrification certainly has its place, but engines are not dead just yet. The first question I'm often asked, and we'll start with a brief introduction to PACCAR, is most people wonder, well, who the hell is PACCAR? and what exactly is it that you guys do? And I'll describe a little bit about who we are and what we do. A little bit about energy, transportation, trucks, and the economy. Some with efficiency improvements, and then some future trends and emerging technologies that we see and we're interested in looking at. So for those of you who don't know who PACCAR is, these are three of the truck companies that are part of PACCAR. Kenworth, Peterbilt, and DAF, which if you're European or have been to Europe, you'll see many DAF trucks running around. All three of them are global brands. And we actually now also make the engines, transmissions, and axles that go into these trucks as well. So we're not only a truck company, but we're also an engine and transmission and axle company, or powertrain. So why trucks? If you're coming from a light-duty background, and most of the folks that I encounter at SAE are primarily involved in light-duty application, trucks are a very different beast compared to light-duty in terms of the load cycle they go through, the demands placed upon them by our customers, and the types of technologies that we have to utilize in order to keep our customers making money. For example, nobody buys our trucks, with the tagline, "Has it got a Hemi?" No one cares. They buy our trucks as to whether or not it's going to help them make money. When's the last time you went out and bought a car for yourself with the idea that this car is going to help me make money? Yeah, I suspect the answer is pretty minimal. But for our customers, that's really the primary reason why they buy our trucks, is that it's a tool for them to use in order to make money. So the cost of inventory, what you see in the slide photo there is intermodal train. And trains are great. I used to work for a railroad once upon a time as well, and an airline. So quite literally my career is planes, trains, and automobiles. Trains are great, but trains are not so good at things that trucks are good at, and that has to do with time-sensitive freight. In other words, just-in-time inventory in manufacturing around the world means that you have to adhere to very tight schedules. That means that you can't have things arriving a day early, a day late, a week late. Some commodities are very, very sensitive to time of departure and time of arrival. And railroads don't tend to be as good at that as trucks are. And the infrastructure. The highway system that we have in the States allows for trucks to deliver door to door. Trains can deliver station to station. Now, if you're a large enough facility, like when I worked for the railroad in Minnesota, General Mills was one of our big customers. Well, they would actually have rail track going right to their grain centers because we were moving enough volume that it made sense to do so. Most places aren't quite that extensive. And so truck traffic really is the most time-sensitive way to move their goods and products. So what kind of trucks do we build at PACCAR? We build a variety of different trucks. The one in the center, though, is the one that we tend to spend the most time and attention on. It's easily the largest segment of what we build, and that's our over-the-road trucks. On the left, you'll see pickup and delivery. We do make them. We're not the primary manufacturer in this sector. I would say there are other manufacturers that probably sell more pickup and delivery trucks than we do, although we do make them. Over the road is where we are the second largest seller of trucks in North America. Between Kenworth and Peterbilt, we have roughly 30% of this market. Line haul tractors, sleeper equipped. These tend to get used anywhere from 500 to 800 miles a day, and they will put on between 60 and 100,000 miles a year. We also make vocational trucks. You've probably seen some of our Kenworth or Peterbilt refuse trucks, cement mixers, dump trucks, things like that. So trucks that go through very digital duty cycles. They're either running a full blast or they're not really running at all. A few numbers for those of you who come from a light duty perspective. Approximately 80% of the US freight tonnage is transported by diesel power, and over 75% of that tonnage is moved at some point by trucks. Oftentimes it's a mix between the rail and trucking, where the rail will move large items station to station, and then the trucks will perform final delivery. And in some cases, the trucks are hauling it all the way across the United States, just in the truck. For example, UPS and US Mail tend to utilize truck traffic because of the time sensitivity and delivery of their business. In 2013, trucks moved more than $11.5 trillion, that's trillion with a T, not billion with a B, worth of freight in the US, equal to almost 2/3 of the gross domestic product. And 43 billion gallons of fuel were consumed in order to do that. They travel almost 1 million miles in their lifetime. We have several engines that will actually go 1 million miles between overhauls. That's a substantial departure from what you would find in most light-duty applications. So our business is very different. One of the easiest ways to understand these differences is the freight efficiency comparison when you look at different modes of transport. For example, I have the automobile, our Peterbilt super truck, and our CSX freight train listed here in graphical form. Now, if you were to just look at the fuel economy, the way that most people are kind of in tune in the US to look at what efficiency means to them in miles per gallon, well, the automobile, a little Nissan Sentra in this photo, looks pretty good. It's 37 mpg, that's not bad. Our super truck is sitting at 10.7 mpg, and that doesn't look so impressive by comparison. And a freight train looks really horrible by comparison, and that's about 1600ths of a mile per gallon. Well, what's so impressive about that? Until you start looking at what we're actually doing with it and the freight that's being hauled. Most people aren't buying their automobiles to haul freight. If you estimate that the average human is roughly 200 pounds, the amount that you're carrying is 0.4 tons. If you have an entire family sitting in that car, that's 1,000 pounds, a little less than a half a ton. If you look at the BTE and then the power to weight, and you get down to the bottom and you see freight efficiency, 14.8 ton miles per gallon, and that's the number that's important to us, is how many tons of freight for how many miles per gallon can we move with our vehicles. Well, we're sitting an order of magnitude ahead of what would be considered a relatively efficient automobile, from 14.8 up to 178 ton miles per gallon. And locomotives are even larger than that. They're at 480 ton miles per gallon. And the big part of that is the power to weight. When you're sitting at more than 100 horsepower per ton, has it got a Hemi, is where that comes from. Performance sells vehicles. Fuel economy doesn't tend to sell vehicles so much. People will tell you that it's important, and then they'll go out and they'll buy the Hemi. In our business, it matters a lot. And the 15 horsepower per ton, again, you're sitting almost an order of magnitude lower than a relatively light econobox type automobile. And in locomotives and trains, you're sitting at less than 1 horsepower per ton. So this basically tells you, where did the investment go? Where does the technology go? We only generate just enough power so that we can pull the freight that we need to pull reliably and with durability at the highest efficiency possible. This is actually our PACCAR integrated powertrain. This is a relatively new product line for us. We now finally have our own internal products all the way down the line, from the engine, the transmission, the aftertreatment, and the axles. So we are becoming a more vertically integrated company year by year. This is a departure from what it used to be in the heavy-duty truck business. It used to be that you ordered heavy-duty trucks kind of like you were ordering off the menu. Yeah, I want this particular truck, but can you get the Cat engine or the Cummins engine? Do you want the Allison transmission or do you want the Eaton transmission? Which aftertreatment system do you want? You would essentially order it right off of a catalog. The regulations and the demands upon our products have essentially made it such that we now have to integrate these products from the ground up. They all have to communicate with one another. They all have to be within the same control scheme. They all have to work and play well with others. And if they don't, we don't tend to meet the emission standards or the durability standards or the customer demands that need to be met. And so it doesn't work. So here, this is essentially the way the industry seems to be going, is that we are now bringing a lot of these technologies with our partners and with our suppliers in-house. For example, the PACCAR transmission was a collaboration with Eaton. The PACCAR engine was done in collaboration with our truck and engine company in Holland called DAF. And we've now been building engines in North America for just over 10 years. So for efficiency improvement, all of these technologies have to be looked at. All the low-hanging fruit over the 100 years of doing this has probably been picked already. So that means that there's a variety of really interesting technologies that are being explored, and it makes it very interesting and challenging at the same time with regard to the integration, the engine and aftertreatment, even electrification and hybridization. Oh, I used the E word. I wasn't so sure I wanted to use that word today, but the E word actually does exist in our business. Electrification isn't bad, but you'll probably notice something a little bit different in the way that we use it here versus the way that folks use it in other applications. One of the big revolutions in our industry here had to do with what you see in the graph in the upper right. The AMT stands for Automated Manual Transmission versus the standard stick shift manual transmission that trucks had come with traditionally. One of the reasons for this was to help optimize the system, the engine, the aftertreatment, the trans, and the axle. And again, because we're no longer ordering off the menu, you can now optimize the engine and the transmission and the gearing to work together for the application that's being purchased by the customer, so that we can provide them the optimal performance and efficiency windows possible. When we bought trucks the old-fashioned way off the menu, simply because you bought a Cummins ISX-15 with an Allison transmission and a different axle, because you thought it would be really cool for high-end torque or something, didn't necessarily mean you were getting the best performance. And the engine was often running in a non-optimal speed load range throughout the entire engine speed load map, because the gearing was all off for it. Now, with the AMTs, we can essentially optimize our engine and the engine maps with the transmission shift points and with the demand that the vehicle is likely to experience. So for example, our vocational trucks are not going to be geared the same way that our line haul trucks are, or the panel van trucks. They all are going to have slightly different optimizations based upon the expected use and based upon the expected demand that they're going to have. Another advantage with the adoption of the AMTs, one of the big issues in our world is driver availability. I'm sure you've seen the ads, you can see them on the back of almost every truck that you pass. Drive for us, we pay more per mile, you'll get more home time if you drive for us. There's a substantial driver shortage with most of our customers. Driver retention is something that our customers are very sensitive to. That's one of the reasons our trucks actually sell reasonably well, is that drivers like driving our trucks. And it's easier for these fleets, whether it's J.B. Hunt or Werner or Walmart, take your pick, for them to retain drivers when the drivers like driving the truck. AMTs have essentially lowered the barrier of entry for people to learn how to become truck drivers. That impression that becoming a truck driver and getting a CDL and doing this for a living was something that was unattainable to a lot of people, that bar has significantly lowered. And the AMT has been a big part of that. And in addition to ADAS type systems that are going into the vehicle, we'll talk about those later. But there are significant driver aids that have gone into heavy duty trucks over the last 5 to 8 years that have substantially lowered the bar of admission to get new drivers to drive the vehicles, because that's something that our fleet customers were very sensitive to. So some of the drivers for that dirty E word that I didn't want to use. Greenhouse gas phase 2 and ultra low NOx. I think everybody in the room is facing these issues, along with the so-called zero emission zones. Zero. When somebody can come up with a really good definition for zero, I'm really interested in hearing what that is, but that's what they call it. Fuel economy, anti-idle systems and stop-start, regenerative braking, stuff that the light-duty guys have been doing for quite a while. Accessory electrification, in terms of energy management, availability even of electrified accessories. And again, remember the electrified accessories for heavy duty are likely going to be a little bit different than what you might see in light duty. Even the water pumps, the oil pumps, these types of accessories, the duty cycle that they undergo is fairly robust. Even engine off coasting. You'll notice that nowhere in this slide am I talking about motive power for electrification. So with regard to where we would use electrification, at least for most of our trucks that are listed here, only at the very end in the what we would call electric drive, and that would be refuse, pickup, and delivery. And those trucks very rarely go over 40 miles an hour. They're almost all captive fleet, and they very rarely go much farther than the average car goes in a year, on the order of 25,000 miles a year. So there are certain applications where electric drive might have some sensibility, but you'll see in 3 of those, there's still an engine involved. And in fact, with the first 2, vocational and line haul, the engine is far and away the primary mover. And in fact, it's going to be a critical part of being the primary mode of drive in those first 2 applications for the foreseeable future. The truck that you see in the hybrid application is one of our DAF trucks. It's the cab over design. And some people, just as a complete non sequitur, have asked us, well, why did the DAF trucks have cab overs and why did the Kenworth and Peterbilts not? And it has to do with the regulations. In Europe, they regulate the entire length of the tractor plus trailer. So in order to meet the length requirement, you put the cab over the engine so that you can put more trailer. In the US, they tend to only regulate the length of the trailer, so we can actually make the tractors more aerodynamic and make them longer because the length of the tractor isn't necessarily regulated. There are market pressures to keep the length of the tractor within a certain boundary, but not necessarily regulatory ones. Funny thing about improving truck efficiency, if you take a look at where the losses actually occur and you're aiming to improve the efficiency of the truck, the big hitter is still in the engine losses. There's still work to do here. And truck engines are pretty good in terms of their efficiency. Our standard MX-13 and MX-11 engines right now for model year 19 are sitting in the ballpark of 47% BTE. And that's for an engine that is designed for the bearings and core engine parts to go 1 million miles. 47% is relatively good when you consider those constraints. But the biggest energy loss is still in the engine, and that is the best place for us to go looking at improving vehicle fuel consumption is in the engine. Obviously the other ones are important and we're looking at those too. But since this is an IC engine efficiency symposium, talking about the aerodynamics of the truck seems a little bit of a reach. So our current engine configuration, and I suspect that this is fairly standard for most of the ones that you find. It's fairly typical. We have a charger, cooler, a turbo, EGR. We essentially package the OxyCat, the DPF, and then the DEF with the SCR and the SlipCat all together in the package that you basically see in front of you. There's nothing esoteric about this. This is the way it currently looks. So the question then becomes, where do we start? How do we start trying to extract more efficiency out of it if most of the low-hanging fruit's already been picked? And you have to take a look at where the energy actually is available. Where is there opportunity for us to recover something or to extract something that we aren't currently extracting? Waste heat recovery systems are certainly one of them that we're looking at. Certainly Cummins is a big advocate of waste heat recovery, and we are certainly looking at waste heat recovery. Waste heat recovery can take on a variety of technologies, though. It isn't necessarily a bottoming cycle. To some degree, a turbocharger is a waste heat recovery system. It just provides an air pump instead of power to the shaft, so to speak. So waste heat recovery can encompass a lot of concepts. But in general, it means that you're taking heat that you would otherwise be throwing away and trying to utilize it in a different way. Improved gas exchange. How can we make the engine breathe better? Part of the losses in an engine have to do with how we get the air in and how we get the exhaust out. So improving the engine's breathing capability as an air pump is part of the ways, because it costs power to do that. It costs power to bring the air in and to get the exhaust out. Reduced friction. I think folks have been working on this ever since they discovered friction was a thing. Reduced friction is always important because that almost always leads directly to improved shaft power. There's very few gymnastics that need to be done in order to translate reduced friction into improved shaft power at the wheel. That's also why it's very difficult to achieve big gains here. Most of the big gains have already been accomplished. Reduced accessory load, and here I think is one of the areas electrification can help. There are a variety of different kinds of gizmos that you put onto the engine. We call the front end accessory driver FIAD, the alternator, the air compressor, the power steering pump, oil pump, water pump, all of these things that are required to allow the engine to operate. In general, belt-driven accessories, even though mechanically they may be relatively efficient, the pumps themselves are very rarely operating at their most efficient point throughout the entire engine speed load map. If you could make those pumps operate at their most efficient point all the time, you would help yourself considerably. Improved combustion, probably the place I've spent the most time over the last 17 to 20 years. There are opportunities in combustion to improve not only the thermal efficiency, but the emission signature. None of them are easy, but the opportunities exist. And engine and after-treatment integration is another big one, and I think you're seeing everybody in this business move to this model. A lot of the companies that are working in this area are doing everything they can to get the engine and the after-treatment to communicate and work well together, because you can't have inefficiencies here when you flunk emissions tests if you do. But this is an area where doing it wrong can really cost you efficiency. So what are the things we're looking at? We're looking at all of the things that are on this particular slide, but like everything else, it always comes at a cost. We're certainly looking at optimizing bowl geometry with injectors in the combustion system. CFD, I think, has made probably the biggest impact in that over the last 10 to 15 years. The advent of really advanced CFD tools and the understanding of the CFD operators and the engine calibrators and engine research people working together, I think has made major impact in this particular area of combustion system development. In the old days, it was kind of flying by the seat of your pants. You did something that you thought made sense. You would kind of visualize what you wanted the bowl to look like, and then you'd go make one, and then you would have the injector company make something for you, and then you give it a try and you run the test and see what happens. Now it isn't nearly so hit or miss. The CFD is much better at allowing us to get a reasonably good prediction as to what these combustion systems can do. Exhaust valves and passages. This is an area, again, that was always fly by the seat of your pants a little bit. And now we're really looking at how we can optimize even things like heat loss in the exhaust port. How do we separate the exhaust manifold heat transfer from the head so that we can retain as much of that heat as possible and direct it into an area that we can extract rather than just letting it radiate to the environment. The turbocharger and EGR system. Those of you that remember the consent decree from '98 and essentially it is essentially a similar thing that happened in 1975 with the American automobile market. The Corvette went from making 300 horsepower in the early 1970s to making 140 in 1976 because of all of the aftertreatment and calibration issues they had. Essentially, it cut it in half. The same thing happened here in 1998 in heavy duty with the consent decree. All of the EGR that the manufacturers threw at the engines caused the power and the efficiency to just fall off a cliff, which we have since regained and then exceeded where we were in 1998. But a good chunk of that was turbocharger and EGR system. So there are still areas to look at for improving in the turbo and EGR system. Of course, the downside is that as we keep chasing higher and higher efficiency, we keep running into physical limits and barriers. And the big one here is higher cylinder pressure and an even higher rate of pressure rise. When I was running gasoline compression ignition at Argonne for quite some time, we used to call it the sound of efficiency. The more violent I could make that combustion event in the cylinder and the shorter that combustion duration, the higher the efficiency. Because the heat transfer time is relatively short, and you're more closely approximating constant volume combustion with a 10-degree burn duration versus a 35-degree burn duration. But it's violent on the hardware. Violent is the right term. Hardware durability is something in this field that is critically important. And so we have to balance our pursuit of efficiency with making sure that these engines are robust and durable enough to always perform for the customer when needed. Turbocharger speed. The turbocharger is getting matched more closely to the engine breathing characteristics. Again, that's always something that was done sort of on the back of the envelope. Now we're utilizing advanced simulation tools to allow us to much better match the turbocharger with the engine, and even utilizing technologies like titanium compressor wheels. Exhaust temperature. Turbocharger material and air management. How are we going to make sure we have enough energy for the after treatment to work, but not an excessive amount? Because every degree that you're giving up in the exhaust is a degree that you didn't extract in cylinder. So it's this constant trade-off between how much efficiency can you chase versus making sure you can always meet the regs. Oil life. Truckers hate changing oil even more than regular people do in their cars. And they don't like sitting around. Why? Because when a trucker is sitting around, he's not getting paid. All of them are by the mile, and if they're waiting for 90 minutes to get an oil change in their truck, it means they're not making dime number one. They really don't like that. Now that I work for a bank that builds trucks and sells them to accountants, I get to listen in on all of our customer service calls and warranty issues and all of these things I never had to worry about at a national account. It's entertaining, to say the least, to listen to the actual customer talk about the product. So not that I necessarily am the one that's solving their problems, but I at least need to be aware of what issues they face. Some of the things that are technologies of interest that I'll talk about here briefly. Turbo compounding, and if you're not familiar with that, it's the power to the crank essentially using a turbo, but not necessarily to drive an air pump. You're actually putting shaft work either to the drive shaft, or in some cases you're turning a generator. But you're using the turbine on the exhaust in order to actually create shaft work or create electrical power. It does indeed improve engine thermal efficiency. The problem always comes in with how are you going to get that power to the wheels. Because if you're going to do it electrically, that means that you have to have on some level an electric drive. If you're going to do it mechanically, you have to have some sort of clutching system, which means that to our customers, more parts equals more things to fail equals more downtime. And again, they really don't like that. So you have to be able to balance what that benefit to them is going to be in terms of the efficiency versus what is the risk of failure or the risk of downtime. Waste heat recovery, bottoming cycles or Rankine cycles, these are really interesting, and you can get them in almost any flavor you like. The change of the working fluid, people have looked at things like water ethanol and a variety of organic compounds, which is why they're called organic Rankine cycles. It's a vapor cycle. You're using waste heat, whether it's EGR coolers or exhaust heat, coolant, in order to drive a turbine in a vapor cycle. As a guy that taught thermodynamics once upon a time, the problem I have with thermal cycles like this that are vapor cycles is that you're paying thermodynamically to vaporize a fluid, but you can't extract it to liquid. You have to have a condenser because you need to be able to pump the fluid around in order to keep it moving. So a lot of that penalty that you're paying, and that's why the efficiencies of these are relatively poor. You know, the grade of the heat is relatively low to begin with, and then a good chunk of the heat that you're putting into the system to vaporize it in the first place, you can't extract all of it back out because you have to keep it vapor as it goes through the turbine. If you doubt this, try running a liquid through a turbine that's designed for vapor, and in very short order, you'll have pieces and parts lying all over the place. It's catastrophic failure. It's pretty entertaining to watch once, but it's not really something I would recommend doing if you actually have to pay the bill for replacing it or repairing it. And then you condense it out to move the fluid around. So there's a fair amount that doesn't get extracted. One of the interesting Rankine cycle approaches is one Southwest is doing using supercritical CO2 because there's no phase change. It's all supercritical phase. So you can actually extract most of the heat that you put into the system, you can get back out. It has a whole bunch of other issues that go along with it, but from a thermodynamic point of view, it's really interesting that you're not paying for the phase change. Thermoelectric and thermoacoustic. Thermoelectrics, I think, have been around for quite a while. I wasn't aware of this thermoacoustic thing until fairly recently. If you're not familiar with it, you can actually do a Google YouTube search, and you'll see these little gizmos running in these little glass vials and these little Stirling engines running on this thermoacoustic principle. It's essentially creating a thermal harmonic vibration, more or less, kind of like a loudspeaker run in reverse. And you can put thermal energy in and get this oscillatory behavior out. And you can utilize extraction methods to actually do electrical power generation with this thermoacoustic gizmo. They tend to be fairly sizable and they're not very power dense, which is a typical Stirling engine. But when you're looking at relatively low grade exhaust heat or coolant heat, it's at least worth looking at in the sense that you're not flowing a fluid. The fluid is more or less stagnant, it just oscillates back and forth as it heats and cools. So it was at least of novel interest in that regard. There's a lot of work that needs to be done, but if you're trying to extract a lot of work, these are things we're looking at. Reducing friction and accessory drive load. I think I covered this a little bit here. That's why we're moving toward downspeeding and electrifying a lot of these pumps and electrical accessories. Cylinder deac and Miller cycle. We're certainly interested in looking at cylinder deac, if not necessarily so much from an efficiency point of view, but from a keep it hot for an after treatment point of view. Not flowing a whole bunch of excess air with engine cylinders running at low load is certainly one way that we can help keep the exhaust hot. Thermal barrier coatings, I prefer to call them thermal swing coatings in that what tends to be insulating also tends to have high heat capacitance, and you tend to lose whatever you gain in thermal efficiency with a loss in volumetric efficiency. But if you can get the surfaces to actually more accurately match the combustion temperature that's in cylinder, there are some gains to be had here. So this is an area we're actually reasonably excited about with some of the latest innovations in materials, where some of the materials do seem to show that they have a relatively good insulation property, but a relatively low heat capacitance. So stay tuned, this is something I think that's worth watching. My favorite topic, farther in the future, advanced combustion or low temperature combustion. You can use whatever acronym you like. There's probably 50 of them, depending upon who's doing it. They tend to reduce the heat loss and reduce the after-treatment requirement. Control can range from challenging to impossible, depending upon the strategy and the fuel that you use. Diesel fuel doesn't tend to be ideal for low temperature combustion, but the issue for us is diesel fuel is kind of like comfort food to our customers. They're familiar with it, they like it, they know where they can get it. It's a combustible, not a flammable, and for some of our customers, that's a big deal. It's familiar and it's available. Other fuels are certainly hypothetically possible, whether it's natural gas. Gasoline would be the easiest crossover fuel. We actually have had customers want to know if they can run their trucks on the red numbers and not the green numbers. Stay tuned. This is all stuff that's of interest. We have management who listen to that kind of a financial point of view. Other fuels, not much interest to us at this time, in the sense that it's got to be something our customer can see at the pump. The engine application choice impacts efficiency. Again, not all of our trucks work in the same type of realm. All of these things are application dependent. I don't think there's a one-size-fits-all solution for all engine technologies. In other words, what works in light duty doesn't necessarily work in heavy duty, or vice versa for that matter. The end result to accomplish these targets tends to be application specific. But I think at the end of the day, there is still significant improvement to be made in engines and fuels to meet the efficiency and environmental goals that we have. We're not done yet. Thank you very much for your attention.
Yeah, I think we have time for at least one question. If anybody has a question for Steve. Please.
Jeff Mustard from the Shuffler Group USA. Thank you for a great presentation. I was just wondering, picking up on your theme of down speeding and the transmission, do you foresee like a possibility for a mechanical CDT type of transmission for heavy duty?
Certainly the possibility exists. I think the challenge in the CDT area, as we've looked at it, is the durability part. Our customers really do pound the hardware, and they have to really be convinced that this hardware is going to work for them all the time. And that's been our challenge with CDT approaches, at least in the past, is getting them to last and not become a maintenance item for our customers has been a hang-up in CDT. And with as many gears as we have in our transmissions, there doesn't tend to be nearly as many spots where the CVT would really outperform one of our current either 12 to 18 speed transmissions in the engine speed load range that's available to us. So I would say probably not the lowest hanging fruit for this particular application. Thank you.
Yeah, please.
Eduardo Barrientos, that's a mobile. Quick question, how do you see the next challenges with the ultra-low NOx from CARB being addressed within your inventory of technologies in the future?
Well, certainly we are paying very close attention to ultra-low NOx and GHG. Regulations are just as important to us as they are to anyone else. I think the challenge in our world, and I think this is a misperception, it isn't that we can't do it, but can we do it in a way that is robust enough for our customers to continue to operate their vehicles the way that they expect? That's where the technology goes, is making it what I call idiot resistant. The world is too full of idiots, you can't make it idiot proof, but you can make it idiot resistant. And getting ultra low NOx targets to be idiot resistant, I think, isn't just a challenge for us. I'll be honest, I think it's a challenge for CAR. I haven't heard an accurate description yet about how they're actually going to validate that a truck does indeed meet 0.02. I get a lot of hand waving, but I haven't heard a really sound technical assessment as to how they are going to ensure that this does indeed meet what they claim the regulation is going to say that it does. So I think all of that is still yet to be hashed out. But yes, we are very attentive to what it's going to have to take for us to meet these standards. Thank you.
Okay, let's thanks Steve one more time. Appreciate it.